So hello everybody, welcome to today's class. This is going to be a continuation of the magnetism class that we started with. Okay, before we start off continuing with magnetism, first I want to point out that there is a worksheet that you can download. This is magnetism 2. Okay, this is different from the magnetism earlier worksheets that we had. Okay, so please do download this worksheet. Today's questions will all be from here. We'll start by looking at these questions. The second point I want to emphasize and explain, magnetism, some of you are finding it a little hard. Some of you have written to me also after the class last week. So yes, it is a little bit hard, which is also the reason I have started magnetism early. Okay, usually we would have done ray optics. After that, I will come to magnetism. But today, this time I want to do magnetism just a little bit. I'm not going to do the whole of magnetism. Magnetism has about four different parts. For example, we are right now focusing on force on a point charge, a moving point charge. Then we will look at force on a conducting wire, okay, current carrying conductor. The next step is to look at magnetic fields produced by wires, and then force between one wire and another wire. Okay, torque on a loop. All these are different things that we will study in magnetism. Lots of applications of magnetism, but we won't look at all of that right now. So right now, I'm just asking you to get introduced to this cross product based force, which is a little bit weird. Q into E is an easy force. Okay, whereas Q V cross B looks like a hard or more complicated force. Actually, it turns out that it won't be that difficult, but it will take some time to get used to, which is why I want you to get started. So today will be the last class of this round of magnetism. After that, I will go back to ray optics. Then I will finish ray optics and then we'll come back to magnetism again. So second round, when we come back to magnetism, maybe we'll do a little bit of ray optics, some capacitance, and then come back to magnetism. By the time I come back to magnetism, hopefully what you have learned now, it will slowly settle into your heads. And then you will be able to see the second time when we look at it, you will find that, oh, it's really easy. Okay, all of these things, unfortunately, have to be learned once or twice. So we are going to go through it 2 times at least. And so what I would like you to do is to just go through this lesson now. Even if you don't get everything, what would have happened is this is the first time you are facing a cross product based force, right? You have learned cross products long time ago, but you didn't have any forces with cross product in it. Right now we are looking at forces with cross product. Magnetism is the first time that happens. And so it's important for you to get used to that idea. Okay, because you have to look at 3-dimensional picture. Most cases we have been focusing on 2-dimensional pictures, whereas 3-dimensional makes things a little bit more messy. Only the image really straightforward. So for us to get into this mode, I want you to get started with this way of thinking. And so that's why 2 classes of doing magnetism now. Then we will go to other topics. We'll do ray optics and so on, and maybe come to capacitance, and then I will come back to magnetism. Next time I come back to magnetism, you will find the same thing that I have taught you now. You will find that it's a lot easier. At that time, we will also go a little further and finish off the remaining parts of magnetism. I'm not going to complete magnetism chapter now. I'm just doing a bit of magnetism, the early parts of magnetism today. Today, we are going to continue with what we did last week. And after that, I want to introduce the idea of force on wires, force on current carrying conductors. So I will start with force on a point charge that we have already done last week, right? So I'm going to continue with that. I will just introduce that basic idea and then we can get started on looking at force on wires. So right now we will do magnetism. This is magnetism second class. Okay, so first let's quickly look at the basic idea. There is something called a magnetic field, B field, which is a vector. Okay, now if the B field vector was like this, and a charged particle was sitting here, you won't have any force acting on it. But if the charged particle had a velocity V naught, right, like this, or velocity V like this, charge is Q, the force on this charge particle is Q into V cross B. Okay, this is a cross product, V cross B. So if you go from V to B, I'm just going to show it with my right hand. Don't worry about it. Use your right hand because you will see that there is a flip that will happen. V cross B tells me that the force must be towards me. When you are looking at it, you will also see, because this is a same picture that you will be seeing. So you should be able to go from V to B. And if you turn your fingers from V to B, you will see that the thumb points towards you. Okay, so you will see that it will be pointing towards you. So V cross B, like that, is basically pointing towards me, or in your case, it will be pointing towards you. Okay, so this is the force, assuming Q is positive. If Q was negative, if Q is positive, direction of force is the same as the direction of V cross B. That is the direction of the thumb. If Q is negative, direction of force is opposite to the direction of V cross B. So it is Q times V cross B, that is the force. So we know this. A lot of questions in magnetism, Q by M comes up. Because, for example, if you want the acceleration vector here, you will get Q by M into V cross B. Okay. So now this Q by M is called basically charge to mass ratio, specific charge. It's also called specific charge. Okay, this is something that is specific to each particle. Like a proton would have a Q by M, electron would have something like, because its mass is 1/2000th of it, its Q by M will be 2000 times that of proton. Okay, so electrons Q by M is almost approximately, not exactly 2000, 1800 and something. Okay, almost approximately 2000 times protons Q by M, because both have the same Q but different M. Of course, you'll have a minus sign as well then, but I'm just talking about the magnitude. Generally, we are going to talk about Q by M. We'll use that a lot. It's usually represented by alpha. We also saw last week when we were discussing this lesson, right? We looked at the... Oh, sorry, I should have taken this and put it somewhere else. Just give me a second. Let's take this, cut it and paste it here. I should have pasted it on the first page. I pasted it on the last page. Sorry about that. Okay, just a second. Okay. Yeah. So this... Right. I should have gone there. And here. Okay, so let us continue now. And so basically the second thing that we saw was what happens when a charge enters a magnetic field like this. Okay, so this is a region with magnetic field, B. And we saw that when a charge enters like this, a force in this direction. So a force like that, and that will basically make this fellow curve around, assuming it's a positive charge. It will curve around and it will exit this way. Okay. Now, the radius of this path, if I draw the radius there, this would be R. Of course, this will also be R. Okay. And if this angle at which it's entering with respect to the region of the magnetic field, if this angle was theta, you know this angle is 90 because the velocity vector, velocity V cross B, you can see that this is perpendicular. So acceleration, which is Q by M into V cross B, is perpendicular to V and of course perpendicular to B. Okay, here I've said B is pointing into the screen, but V here like this. So it tells you that the force is perpendicular to V, acceleration is perpendicular to V. That is going to also tell you the radius direction. So we saw that if this was the center, this is R, this R vector and V are basically perpendicular to each other. So this is theta, this is 90, this is 90 minus theta. And so if I drop a perpendicular, this will be theta. So we saw that this was R cos theta, this is R sin theta. So 2R sin theta will be this distance. So you saw all of that. We also saw that the radius, you can calculate how do you get the radius by saying QVB, which is QV into B, QV cross B, V and B are perpendicular. So QVB is equal to MV square by R. So that tells us V by R, is QB by M, because you can cancel out one V. Okay, so QB by M is V by R, but V by R is omega because velocity divided by the radius, that tells you the angular velocity. So the angular velocity is not dependent on the speed V with which it's entering. It is not dependent on the radius. It's just dependent on Q by M, which is alpha times the magnetic field. We saw this. And from this, we saw that the time period of revolution must be 2 pi by alpha b. So we saw this as well. And of course, from this, you can also calculate what is R. And so R is just going to be mv by qb. So we saw all of this. Okay, so this is the motion of a charged particle in a magnetic field where the plane of its motion is perpendicular to the magnetic field, or the velocity vector was perpendicular to the magnetic field. So the plane of motion is going to be perpendicular to the magnetic field. So we saw all of this, right? Now the question then is, what happens if you had a situation where the magnetic field was, let's say, like this. This was the direction of the magnetic field, and this particle, instead of being perpendicular, moving perpendicular, was moving like this. Velocity was in this direction. Then what would happen? So first of all, if the charged particle has velocity like this, you can resolve that velocity into two parts. You can talk about this velocity, which I'll call, let's call this b in the x direction. So I can call this vx, and I can talk about another velocity, which is, right now I'll call it vy, but it's basically v perpendicular. So this is v perpendicular and this is v parallel. Okay, let's use the symbol v parallel, parallel to b, that is v perpendicular to b. Now you know that if there is v parallel cross b is going to be 0, because two parallel vectors, the cross product is 0. You can think of v vector as v parallel vector plus v perpendicular vector. And force F, which is Q v cross b, the only thing that will matter is not the v parallel, because v parallel cross b will become 0. So you'll only end up getting v perpendicular cross b. But this you already know, this is perpendicular to this velocity, and the force is going to be like that, perpendicular to both v and b. So the force is going to be in this direction, acceleration will be in this direction, and so basically this is going to make this fellow, or it's either this direction or that direction, doesn't matter, that direction. Okay, so because v and b, if I resolve, so think of it like this, v and b like that, and then the force is going to be in that direction, v cross b, so that direction. Okay, so that is the direction of the force. So it will bend like this. So this is going to make the particle go around in circles. Okay, but we are ignoring v parallel, right? So while this fellow is going around in this circle, what is going to happen is that this circle is going to start moving like this because of v parallel. So imagine that you are moving around in a circle like this, but the circle itself is moving forward. So what is going to happen then? So imagine that this is the situation. So if I had this circle, and now this circle was moving from here till there, was moving from here to there, and so on. Well, obviously it's not going to go in a circle, right? Because what is going to happen, as the charged particle is moving around like this, it has also moved forward. So it is going to go around like that, and by the time it comes back, this is where it's coming back. And then it continues going around. And as it's going around, it's supposed to go in a circle, but the circle itself is moving forward. So this is actually a helix. This is not a spiral. Please remember, some people confuse helix and spiral. This is a spiral. A spiral is a planar object. You can actually just move on the plane. I can't draw a helix very well, because a helix, if it starts there, it's going to come out, it's going to come in like that, but it's not becoming bigger or smaller. Okay, so it's actually just a circle, except first turn, as you're turning, this plane is moving forward. So imagine that you start there and you keep doing this. So this, the radius of the circle does not change. Okay, so it is moving forward because of v parallel, that is what is dragging this along, but it's moving in a circle because of v perpendicular. So it is actually a combination of these two motions. So it is, think of it as going around in a circle, but as it's going around in a circle, the whole thing is also going forward. Very, very interesting motion. So this is what it's doing. This is three-dimensional. You have to understand that it's going forward like that and coming back like that. Understood that? Okay. So then, can I figure out the radius of this circle? Can I figure out what is the radius of this circle? Yes, you can. Because this circle's radius Okay, so if you take the helix and collapse it, you will get a circle, right? That circle's radius is determined by this, except instead of V, remember that here we have got mv by qb, same thing, except the radius of the circle is mv perpendicular by qb, because V perpendicular is what makes it go around in a circle in the first place. Okay, but it's not in a circle. Why is it moving forward? Because of V parallel. So in one time period of going around like this, basically what is going to happen, where it should have come back to the starting point, instead of coming to the starting point, it will come back to the starting point there. Because while it went around like this, actually it was also moving ahead. So it would have gone around like that and then come here. You have to understand that this is three-dimensional, so this is behind. Okay, so imagine this line. I'm drawing it like it is two-dimensional, but basically think of it like this. It went round and it came back to the same point here, but by the time it came back, it is now a little ahead. So usually we call this the pitch of the helix. Okay, pitch of the helix. That tells you how much you have moved when you made one full trip. Okay, is that easy to find out? Well, you know the time period of motion, t. So in that time period, how much you would have moved? You would have moved v parallel into time period, because there is no force along the b direction. So it's constant velocity. Does it remind you of something? What does it tell you? Like, for example, if you have projectile motion, horizontal velocity does not change, only vertical changes. Now it's slightly different. The component along B does not change, but the other one is going to make it go around in a circle. So it is a circle superimposed on a linear motion. In the other case, in projectile motion, it was accelerated motion imposed on a horizontal velocity, right? Constant velocity. So you're supposed to come down, but you're not coming down straight. While you're coming down, you're also moving to the right. So that's why you went in a parabolic path. Here you're going in a helical path because it's two-dimensional. You're going in a circle, and the circle itself is moving forward. So I hope this is clear. How to do calculations, problems with this, when we get down to doing that, we will see. Right now, that's it. I would like you to start solving question number 1 from the worksheet. I'll just focus on a few questions. Question number 1 should be straightforward. It is exactly like what we did last week. Question number 2, a little bit more tricky. Please try question 1 and then question 2. So I would like everybody to try question 1 and question 2. Then we will discuss it. After that, similarly, I will do question 3, question 4 using the theory that I just taught you there. Okay. So, but first do question 1 and question 2, and then we will discuss these two. Okay, Rohit has, not Rohit, Ribhav has asked a question. Okay, Ribhav's question is, earlier we saw that if a charged particle enters at an angle, it just goes back making a sector of a circle in the magnetic field. In the plane, see, remember the velocity, this is the way the charged particle is entering. See, like if you look at the velocity of the charged particle, it's so many possibilities. But if the magnetic field was perpendicular to the velocity, okay, the field, this is the region of the field. It is entering like this at an angle. Instead of entering like this, it is entering at an angle to the region of the field. So, but the velocity is still perpendicular to the magnetic field. So the force is like this, and therefore it turns around like that. Okay, let me just show that to you. So this is different from what I just explained. Okay, so that's why this is slightly complicated because of the three-dimensionality. So basically, the earlier situation that we saw, this is the region. The velocity is this way. It is entering like this at an angle. But the magnetic field is into the board. See, the direction of the magnetic field is into the board. So the magnetic field is perpendicular to the velocity. And it is going to go like this. Okay, this is just a sector. Like you're saying, this is correct. But here, the velocity is perpendicular to the magnetic field. There is no component of velocity along the magnetic field. Now, the only problem is I cannot show you this and also show you that direction, right? Now, just imagine that this velocity, instead of being like this, was bent like this. The magnetic field was like this, velocity is like this. There are two components. One component is this way and one component is that way. I hope that is clear. Okay, so let me show that to you carefully again. So the velocity vector, earlier remember I showed you this. Now this is making an angle, make region. So this is our region. The magnetic field is on that side and it is making an angle with this region, with the boundary of the region. Okay, but the magnetic field was like this. Now imagine that this fellow has a bend like this. That means there is a component along the magnetic field and there is a component perpendicular to the magnetic field. Then what is going to happen is the component along the magnetic field won't matter for the rotation, right? It will continue to go around like this. But as it's going around like this, it is also getting pulled in because it has a velocity. So that velocity is not changing. So it is getting pulled in. And so that is the big deal. That is the difference between what we just saw. Okay, this is, see, look at this. Here it is just completing a sector. Whereas here, the magnetic field, now I've made it go along in this direction. Only then you'll be able to see there is a velocity component along the magnetic field, and then there is a velocity component perpendicular to the magnetic field. So that's why I showed it like this. If I had shown the magnetic field as pointing into the board, like this, and the velocity had a component along this, then the helix will be like this. So it will still make a round. And for example, now imagine that this boundary is not there. Just let's imagine that there is no boundary. So everywhere you have magnetic field. So it won't make a sector, right? It will just go around and make a full circle. But now there is a component of the velocity inwards also. So while it is doing this, the circle will be coming closer. So you start with the circle like this, then get closer and closer and closer and closer like that. Closer to the screen, I mean. Okay, closer doesn't mean anything. It just simply means moving forward. So I hope that is clear, Ribhav. Okay, so that was Ribhav's question. I hope that was clarified. Rohit has said, sir, you told in the video lectures that force is felt by the wire and not by the current. But doesn't force be exerted on charges of current? Good point. The force is exerted on charges. Okay, but ultimately the charges are constrained to be in the wire. Why is there a constraint? Because obviously the charges cannot run out of the wire. Okay, so this is something a little later I will focus on, Rohit, where we are looking at force on a current carrying conductor. It is felt by the wire or the conductor and not by the charge. Here, of course, the charge feels the force, but the force has to be transferred to the wire. You can't transfer force to a current. Current is just the flow, right? There is no physical thing called current. So therefore, you can't really transfer the force to currents. You can transfer force to the conductor. Anyway, that's something that we will look at little later. Quite a few of you have answered question 1. So I would like us to start with question 1 and then maybe we can go to question 2 after that. Okay, I'll give you time for 2. I want to just first finish question 1. Let's first quickly finish question 1. If you have doubts, please do ask on the chat box. not on the chat box. They will post a separate box like the question box. You please post it on that, so that way I will be able to address those questions more clearly. Let us look at this question. So in this question, there is a region. This question, there is a region of magnetic field, which is this side. This side has magnetic field. Okay, so let us mark it. This everywhere here, there is magnetic field B. And the magnitude of the magnetic field is given. It is 1.5 Tesla. Okay, it's uniform magnetic field. A particle is entering this magnetic field like this. Okay, so I'm just going to draw it like that. And it makes an angle not with the region of the magnetic field, but with the perpendicular to the boundary. See, there is a region of magnetic field. Now there is a point which surface like this, which you can call as the boundary, because the magnetic field only exists here. The magnetic field does not exist there. Now you can say, it need not be like this, right? This is a semi-infinite boundary, but it's also possible that this could be the boundary. You can have magnetic field only inside this. How will you do these things? Well, you can take a magnet, very powerful magnet, North Pole, and usually, let us say that you have a South Pole here. The magnetic field lines are all here. So this is telling us here is the magnetic field, region of magnetic field. Usually, for example, if this shape was a nice circular shaped, this is a horseshoe type of magnet, but these borders were circular, then you can say that this boundary is also circular. Well, there will be a small amount of aberration here, because there will be a little bit of magnetic field that is kind of going that way. But we will ignore such things. So we'll say this is basically either a squarish shape magnetic field region or a circular shape magnetic field region. There is also depth, it's a volume, right? In this region, that's why we call this a region, you have magnetic field. The same way, let us assume that we have somehow managed to create a region of magnetic field, this entire region, where you have lots of arrows of magnetic field lines like that going around, but it is not going to go into this part of the region. It won't be in this part of the region. So here there is nothing, there is magnetic field only here. That means this is the boundary, and the boundary is like a surface like this, right? So now it's a normal to the surface, which is like that, and the velocity vector is going to make an angle with the normal to this surface. So that's basically what we are showing here. So here is the normal to the surface. One second. And the velocity vector, it is given that this velocity vector is making an angle of theta. So there's a charged particle that's coming in, Q, and it is basically making an angle theta like this, with the normal to the surface. Now you know that as soon as it enters, it is going to start curving around in a circular path. Now you can see that this velocity is perpendicular to the magnetic field, right? The velocity enters a region, particle enters a region, and it's not mentioned it is perpendicular, but it is in this plane. So it's going to just simply make a curve around like that. I should have mentioned that it is perpendicular. Okay, so let us first draw the perpendicular to the velocity. So this is the perpendicular to the velocity. And this somewhere here is the center around which this whole curve is going to happen, right? And do you know where the center must be? So let us say that the center must be somewhere here. Okay, so this is our center. This length should be R. And you already know how to calculate R. Now, this is not in the region of magnetic field, but doesn't matter. The moment you go inside, you know that this fellow is going to basically say mv square by R is QVB, right? It is going in a circle. The circle's center could be outside the region of magnetic field, doesn't matter. The force is QVB and the centripetal force must be mv square by R. The center of the circle need not be in the region of the magnetic field. Okay, so once I cancel this out, from this I can find out that, what is it? R is mv by qb, mv by qb, we already know this. And you also know that omega, which is v by r, is qb by m. So we know both of these. And let us therefore draw how the arc of this circle is going to look. So basically this is going to start like that. It's going to go this way. It's going to turn around. And somewhere there, it is going to come out. Right? So when it comes out, it's going to look like this. It's going to come out in a straight line, moving in a straight line. Okay, so I've not drawn this C very well. So let me just erase this C and replace the C somewhere here. I think this looks more like C. This is more C. Okay, and so this is also R. This distance is also R. So this is also R, that's also R. But if this is theta, think about it, this is 90 degrees. So this must be 90 minus theta. This must be theta. And so if I drop a perpendicular here, this is 90 minus theta. So is this. This is also 90 minus theta. By symmetry, you can see that. Okay, right. So now once I've got this far, this is 90 minus theta, that's 90 minus theta. The total angle here is 180 minus 2 theta. Anyway, this is R cos 90 minus theta, and this will be R sine of 90 minus theta. Okay, but R sine of 90 minus theta is R cos theta. So this is R cos theta, and this is also R cos theta. Okay, let us now start putting in some numbers. And we have been told Q by M is 10. So omega is Q by M. So how much is Q by M? That is 10 coulombs per kg. B, how much is B here? B is 1.5 Tesla. Okay, so that tells us that this is 15. Omega is 15 radians per second. Radians per second. But I don't even need all that. So the question was only asking me is what is D? Well, D, right, this distance is 2R cos theta. And 2R cos theta is 2 times R, which is mv by qb, mv by qb, into cos of 90, like cos of theta. But theta is the value angle given? No, into cos theta. It's cos theta. And we don't want even D. We know D. D is 8 meters. So this D is given. This distance is 8 meters. So I can just substitute all that, bring it down and say cos theta is 8 into QB M, right? Sorry, this is not MQ, it is MV. I made a mistake writing that. This is MV by QB. Here, MV by QB. It's 2R cos theta, right? So this Q goes up, M goes down, 2 goes down, V goes down. I can just substitute all the values. 8 by 2, of course, is 4. Q by M is 10. B is 1.5. And V, velocity V, is 100 meters per second. And so that basically tells us this is 4 into 1.5, 6 by 10, which is 3 by 5. Well, if cos theta is 3 by 5, sin theta is 4 by 5, and theta must be 53 degrees. So from this, we get theta is approximately 53 degrees. Well, that's not exact angle. Okay, so it's approximately 53 degrees. So I hope this is clear. That is the angle at which this must be entering, 53 degrees. If it is given that this distance from here to there, D was 8 meters. So that is given. So just simply playing around with this information. That's it. Is that okay? Can you now go ahead and start looking at question number 2? So can everybody please do question 2 now? Okay, then if you have done question 2, go to question 3. In question 2, unlike this situation, there is a quadrant that is filled with magnetic field. Only this place has magnetic field. So if you're entering like this, you'll start going around in an arc. If this was large enough, it would have come out here. But since it's not large enough, it will come out like that. Okay, so it enters here and comes out like this. So once you realize this, that's basically drawn in the diagram already. You have to use this information to find out the distance up from the point. Let's call this the origin if you want. So distance from the origin where the charged particle is entering. Basically, you need to find this distance D or OP. That's the distance you need to find. So please do question 2. I'll give you a minute. Okay, or a minute and a half. So once you have done question 2, we can start discussing that. Okay. Meanwhile, there are a couple of people who have asked doubts. So I'll just go through the doubts. Some of you want me to solve question 2 from the test paper, which I will do. I'll do question 2 from the test paper. Most of you have got question 1 right, which is reasonably straightforward one. So I think that's good. Vaishnav Sudesh has asked, will the force due to magnetic field do work when charges move in a helical path? Never. Never. Okay. Because remember that V is perpendicular to the force. Now, if you say it is perpendicular to V tangent, V perpendicular, it is also perpendicular to V parallel because it's perpendicular to B. Force is perpendicular to B. The helical path, the V parallel is also in the direction of B, right? So anyway, that is not going to contribute to any amount of work. So always the velocity, the overall velocity is perpendicular to the force because it's V cross B. Therefore, you will not have work done by magnetic field at all, ever. Okay? Both components of velocities are still perpendicular. Exactly. You also answered it correctly. Vaishnav Sudesh is right. So both components of velocity are perpendicular to the force. Therefore, no work done. Ritika Somi has asked, are bodies in magnetic field always in circular motion as force is always perpendicular to velocity? You're talking about charged particles, I'm assuming, not big bodies. Okay. So if you're talking about charged particles in a free floating space, right? There's no gravitation, nothing. Because suppose magnetic field is one force. There may be other forces acting. So since there are so many forces acting, net force may not be perpendicular to velocity. In which case, it may not move in a circular path or a helical path. It may also move in some paths like this. There are cycloidal paths and so on. If there are other forces, like electrical forces could be acting, gravitational forces could be acting. But suppose you have only magnetic forces. Will it then move in a circular path? Uniform magnetic field means it will move in a circular path. But sometimes you may have non-uniform magnetic field. So it starts moving like this, but then the magnetic field makes it curve around. So it could move in a spiral path. It could move in curved paths. Okay. In a way in which the velocity is always perpendicular to the magnetic field. Sorry, perpendicular to the force is always perpendicular to the velocity. So it will not change its speed, but it could move in a curved path because the magnetic field may be non-uniform. So Ritika, I hope that is clear. Savita has asked, why is the answer in sine? For the first question, answer is not in sine. It is in cos. Cos of theta is 0.6. So just root of 1 minus cos square theta. So if you have 3 by 5 is cos theta, you know sine theta must be 4 by 5. We remember that more easily. Sine 3 by 5, sine 37, 3 by 5. Okay. Sine 53, 4 by 5. So since you remember it, I'm using sine. You could also done cos directly. So cos theta is equal to 3 by 5. Therefore, theta must be equal to 53 degrees. That's it. Cos inverse of 3 by 5. So I hope that is clear, Savita. So hopefully people have started doing question 2. Let's see. How many have done question 2? Not yet. Okay, people, please do question 2. I'll give you a minute more and then I can start solving. So question 2, so far I've got 19 people have answered, but only one person has got it right. Sankrit has got it right. Others have not yet got it right. I'm not asking for angle. Ayushi, I think you wrote the first question's answer in the second question. Okay, you written 53 degrees. That is for the first question. So the second question, so far, its answer is in meters. Answer is in meters. Okay, so only one person has answered it right. So I'm going to give you some more time. I'll give you about a minute and a half more. Please do complete it. Try it out. It's a nice question. Okay. Now, so far, it has not come up in IIT entrance. And JEE mains will not ask you this kind of a question. Very rare. Very, very rare. Okay. But IIT advanced, JEE advanced may ask you this question. NEET will not ask you this question. Unless it has already come up in IIT once and then comes up in JEE mains, it won't come in NEET that way. So you don't have to worry for NEET. You don't have to worry about this question. The first one you have to. First question will be there. The second question was not very difficult. So a small variation of this might be asked. Just think about it. The time is given. Arc length and angular velocity, you know what is the connection. R theta is the arc length. Okay. Or theta by omega will be the time it takes to make travel around an arc. Like 2 pi by omega for a full circle. Now you have an arc length which has, let's say, some angle theta. Okay. Whatever that angle is, you have to check the angle. That angle divided by omega. Omega is constant. So therefore you can use that. So try it out. I'm going to give you about a minute more, 1.5 minutes or something more. So please do try it out. Okay, as most people got this wrong, I've asked Kushali to basically post one more box. Okay, so Sankrit, you can write your answer again if you want, but otherwise, everybody else can again get a second attempt. Do try it out. I'm going to give you a little bit more time. I think people seem to need a little bit more time for this question. So I'll give you another about a minute more. Okay, 1.5 more minutes. So please do try it out and enter the answer. Okay, because it's definitely a useful question for us to try out. So every year IITs give something new. So it'll be good if they gave this kind of a question next time. But it's not very tough actually. It's quite easy. So, but if you had a little bit of practice, it'll be useful. I will just draw the diagram alone here. So don't worry, I'm not going to solve it. I'm just drawing the diagram. I'm giving you time to solve. This is just a diagram for myself. Okay, so this is question 2. And let's take So this was not given in the question. I'm just drawing this as a clue. So those of you who want, you can use this as a clue. This must be the center, right? This must be the center. This must be radius r. That must be radius r, because it has to be perpendicular to the initial velocity. It must also be perpendicular to the final velocity. And we have been told that the angle at which this is entering, this angle is theta. Let us just say that this angle here is alpha. Okay, so I will just draw like a line here and call this angle as alpha. Alpha is not given. I'm just calling that alpha. Use this to find out what is this distance d. That's basically the question. So please do try it out. I'm going to give you, it's just a little bit of geometry question actually. It's not so much physics as it is geometry. You know certain basic things, right? QV by MB is R. So that of course you know. So in fact, I will even write that formula down here. So you can see that. You can see that we have done this. I mean, everywhere that's what I've been doing. See, right? R is MV by QB, not QB by this thing. R is MV by QB. I don't remember the formula much, as I guess you can see. Okay, so R is M. What do we get as R? R is, I always keep forgetting, MV by QB. Real bad memory. Okay, and omega is QB by M. QB by M. So these are the two things that we already know in general. So use this information and this diagram and try and solve. Okay, I'm going to give you a minute, just about a minute. Last 1 minute, okay? We've been taking too much time for this question. Okay, Skandan Subramaniam has got it right. And Anirudh Bharadwaj, almost, I think that's the same answer. That's what he's also got it right. Nikhil has also got it right. Very good. Gifton has got it right. Okay. Others have not yet got it right. Okay. Kevin will close. I don't know if that's what you got. Okay. But anyway, can you all please, those who have not yet finished, please do try it. Those who have got it, please go on to the next question. Start solving the next question. We will wait for another 30 seconds and then get started now. Okay, I think we have spent enough time on this question. Let's get started. So in this question, what is given in this question is not like, see, let's think about it. What are the things that are given? It is given that q by m for this question. So the particle is entering like this. And so as it's going to curve around like this, it should have curved around and come out like this, right? But the problem is before that, the magnetic field has already basically, the region of magnetic field has ended. So it has to come out on that side. It's not coming out here. It's not coming out like this. It is coming out like that. So obviously this point has to be reasonably close to the origin. This is the origin. So it has to be reasonably close to the origin. Okay. So let us think about how to solve this. Well, if this angle is theta, this is 90. This is 90 minus theta. So if I draw a perpendicular like this, if I draw a perpendicular like that, this angle is theta. Okay, so let us just draw it better. So this, if I draw a perpendicular like this, then this angle is theta. So I hope that is clear. Theta, 90 minus theta, theta. Now if this is alpha, this angle is 90 minus alpha. So therefore this is going to be alpha. And then you can see that line and this line are basically parallel to each other. And therefore this is alpha. So the total angle it is turning from here to there is theta plus alpha. Theta plus alpha. Okay. This is a quadrant. Remember, this is 90 degrees. It's not necessarily to specify. This is a quadrant is given. Region, a quadrant shaped region. Quadrant would have a 90 degree, right? Clearly. Now, this is the direction in which this is the path that it's moving in. So how much time will it take to move here? Well, the angle is theta plus alpha. Total angle covered, which is the turn, the amount it has turned is theta plus alpha by omega. Now, omega is QB by M. So we can calculate what omega is. QB by M. Q by M is given. Q by M is 25 coulombs per kg. Okay, into B, magnetic field B is also given. It is 0.01. So it is 0.25 radians per second. We can think of it as 1/4 radians per second. That is omega. So that means 4 times, this is 1/4, right? This is 1/4. So that means 4 times theta plus alpha, because divided by 0.25 is into 4. Do you know how much time it takes to go around from here to there? Well, it's given that it takes pi seconds. Pi seconds, which means theta plus alpha is pi by 4. But we've already been told that angle theta is 30 degrees. 30 degrees is pi by how much? 6, right? 180 by 6 is 30. So pi by 6. So that basically tells us alpha is pi by 4 minus pi by 6. This is 3 pi by 12, 2 pi by 12. 3 pi minus 2 pi is 1 pi. So pi by 12. So alpha is pi by 12, which is 15 degrees. Remember, for all our calculations, we cannot use degrees. So like here, we have to use radians. Okay. Theta is pi by 6 radians. For all r theta kind of calculations, we'll have to use omega, r theta. It's all radians. But finally, to understand, we can basically use degrees, right? So pi by 12 is basically 15 degrees. It's pi by 6 is 30 degrees. This is 15 degrees. Okay. Now, I want this distance, right? I want this distance. So this distance I can think of as this distance from here to there, this distance, plus this distance. Okay. So let me just redraw that, this distance. And just to kind of complete our line, let's just say that this is the line that I can extend. It's the same straight line from C. Okay, it's perpendicular. Now, do I know this distance? Do I know this distance? Yeah, r cos theta would be that. So this would be r sine theta. Similarly, this is r, radius r. R cos alpha is this. So this length is r sine alpha. So the total distance starting there and ending here is r sine alpha plus r sine theta. So d, the distance d is r sine alpha plus r sine theta. So that is r into sine alpha plus sine theta. R is how much? We can calculate what r is. R is m into v by qb, right? Now this we can basically write qb by m. qb by m as omega. So I can write it like this: v by omega. R omega is v. Okay. So do you know what the velocity v is? In the question, does it say what the velocity is? It's 10 meters per second. And omega we just calculated is 1/4 radian per second. And so if I multiply these two, I get r is 40 meters. R is 40 meters. And so let us use this r here. So 40 times sine theta. So let us say sine 15 degrees. Let's say 40 times sine alpha, sine 15 degrees, plus 40 times sine theta, which is of course half. So this is going to give me 20. Now what is sine 15 degrees? Sine of 15 degrees, you can write that as sine 45 minus 30, right? Sine of 45 degrees minus 30 degrees. You can calculate what that is. So that sine 45 cos 30, sine 45 cos 30 minus cos 45 sine 30. Okay, so it's root 3 minus 1 by 2 root 2. And so if I write 40 by, instead of writing root 3 minus 1, I can write it as root 6 minus root 2 by 4. So that then this will cancel out, becoming 10 plus 20. So that gives us 20 plus 10 times root 6 minus root 2, which if you did the calculation with root 6, root 2 approximation, it turns out to be 30.35 meters. Okay. Now, of course, you could have just left it like this. You could have said D is equal to 40 times half plus sine 15 degrees. But since you're supposed to know how to calculate sine 15 degrees, people can expect you to get an answer plus 10 times root 6 minus root 2. Okay, so you should be, because if this was one of the options given, you should be able to get this. But of course, if you just look at this, you can write the answer as 20 plus 40 times sine 15. You can also do an approximation. You know that sine 30 degrees, it's a small angle because it's only pi by 6. Pi by 6 is a reasonably small angle, right? 3 by 5, 0.5. You know this is approximately, this is not approximately, this is equal to half. Sine 15 degrees in radians must be half of sine 30 degrees. So that must be, if I think of this as approximately theta, because this is also pi by 6, right? So this answer must be pi by 12, but pi is like 3 by 12, 1 by 4. So the answer must be about 0.25. You can think of it as almost 0.25. So this is 0.5, this is 0.25, 0.75. So 40 into 0.75 is approximately 30. So you can look at the answer that is close to 30 and mark it. If you have multiple choices, this could have been an option that you can quickly mark by saying, I know that sine 15, small angle, already this is a half, this is 1 by 4. 1 by 4 is reasonably small. It's not as small as we would like. It's not like sine 1 degree. But if you did an approximation and said pi by 12, sine of pi by 12 must be close to pi by 12. Pi by 12 is 0.25. And therefore, once I know that this is almost 0.25, this is 0.5, 0.75 into 40 should give me an answer. Quick approximation. If you wanted to do the full calculation, of course, that is how you should go about it. So I hope that is clear. Now I would like you all to try out question number 3. Okay, please try question 3 and then question 4. Try these two out and then I will start solving. I'm going to give you, because it's a helix question, I'm going to give you a little bit more time. So I'll give you like 2 minutes for each of those questions. Come on, quick. Vedram has asked whether there's an easier way to do this question. I'm not sure there is, Basically, it's not very difficult. It is r sine theta plus r sine alpha. The only problem is finding alpha, because theta you already knew. R was easy to find. Okay, so that means you need to find alpha, which is what I've done here. Okay, because time is given, theta plus alpha by omega. So if you think about the steps here, they're not too complicated, because the main steps that are there in this question, if you think about that, time is given, it's pi. Theta plus alpha by omega. I just did a little bit of work calculating omega. You could have left the answer as, once you have got this, right? This step is important. R was easy, 40. Sine theta plus sine alpha. Sine theta was also easy because it was given. So only thing you need to find is alpha. And you've got theta plus alpha by omega is pi. So multiply pi into omega. So that's pi by 4. Pi by 4 is equal to theta plus alpha. So alpha is going to be pi by 12, 15 degrees. Once you got that, all you're saying is to say r sine 15 degrees plus r sine 30 degrees. That's it. R you already know is 40. So it's not, I don't think it's a very tough question. It's not very easy, I know. A little bit of work. The calculation sine 15 degrees probably took me more time. And then the final answer calculation took more time. But if you leave that out, the actual problem itself, the physics of it or the calculation part even, is reasonably straightforward. Till r into sine theta plus sine alpha, I hope everybody is going to get. The small trick part here, you want this length. Right? You want the length from here till there. This part was easy. This length is the same as that length. So that is something that you need to be able to calculate. R cos alpha, R sin alpha. So that is something that I've been repeating from last year. So hopefully everybody knows how to do that. Okay. Whenever you have a line like this, you know this line, you know this. You know the vertical and you know the horizontal, or you know the two perpendiculars, R sin theta, R cos theta. So that's something that we'll have to keep using. So hope that part is not difficult. So now everybody please do question 3 and 4, please. Why can't, Siddharth Balaji is asking, why can't we apply D equals 2 mv cos theta by qb? Okay, he's asking the D question. That was done here. Like we did here, right? So this distance, like here also we have done. Where is that D? I thought I would derive some D here. Here. R cos theta, R sin theta, right? So we have done this thing saying, I think in this question only. Here we have done this, right? So we did this thing where D equals 2R cos theta, 2 times mv by qb cos theta. So this step, the problem is in this step, it's coming out from the same side. Okay, so we have to be very careful about it. This is the region. If this was the region, this is the velocity. This is going to start turning and it's going to come out like this. But if here itself my magnetic field ends, that means there is no field there for you to actually go around like this. So this portion does not exist. So this is where it's coming out. And once it comes out, it's not going to curve anymore. It's going to go in a straight line. If it was like this, you can say that the angle at which it is incident is equal to the angle at which it is coming out, it's exiting. This angle is equal to that angle. The usual angle of incidence is with respect to normal. But basically, if you think of this angle as theta, that angle is theta. But if I think of this region, it is entering like this and exiting like that. It is not even symmetric. Okay, so if this angle was theta, why should this angle be theta? Or this angle be theta? It is not, no? This could be something else, x. I had just called this angle as alpha. And it turns out alpha is not equal to theta. In fact, this angle was 75 degrees. That angle was 15 degrees. And this was 30 degrees. So it's not symmetric. You cannot use that formula. So this formula is only valid. The formula is only valid if it enters like this, turns around and comes back. Is this important and useful? Yeah, this will land up. This question will land up quite often. So it's good to know that. Should you remember the formula? I don't even remember this other formula for R. Okay, so I won't suggest that you should remember this formula. My suggestion is to calculate it. So you start with R, because this may be, sometimes people give this as theta, sometimes they'll give that as theta. So we don't know what they'll give as theta, right? So do this. This is theta, 90 minus theta, theta, 90 minus theta, R cos theta. This is r cos theta. So 2r cos theta. But in the usual formula, this is given as theta. Therefore, you will get 2r sin theta. It doesn't matter. D equals 2r sin theta, 2r cos or sin theta, depending on which you call theta. But this you can just simply calculate. No, this is length and that length. But then in a slightly more complicated question, and that's exactly what JEE Advanced will do, because they know many people will remember this formula, so they'll just turn it around and change it to this. What if they change it to something like this? That is going to be really complicated, right? Because then it's going to go out and it's going to go around like that. So we can still do, but then this angle is alpha or this angle is alpha. You have to use that and then find out what is this is, let's say, the center. Okay, so what is this angle that it's turned by and all that? Little more messy. I don't think this is ever going to come, at least not until this has come. So if IITs are going to give you a question, it will probably be this. And if you finish this question, then they may kind of, a couple of years down the line, they may start saying, okay, let's give something even more complex. But at this point, they won't. Okay, so at this point, this will be probably the most complex question that you might get of this variety. Okay, so now can everyone please do 3 and 4, please? Helix, is it there in the syllabus? Yes, it is there. Okay, Pragalya is saying, I cannot understand how to find the center of the circle. Pragalya, remember one simple thing. The radius, the line, where you have to have the center, has to be perpendicular to the velocity. So that's very simple part. Okay, so let me just show you that. If I told you that this is the velocity, then at the point of entry, let's say that this was the point of entry. Okay, so don't worry about the point of entry. This is not even important. Okay, in fact, I should move on to delete stroke. Yeah. So if that is not important. What is important is that the center must lie on the perpendicular. At any point, if this is the velocity, the center must lie here. But where exactly does it lie? Will it lie here? Well, it could. It could lie here, it could lie there, it could lie there. But we know that wherever it lies, the radius must satisfy that formula that we have been using. mv by qb. Okay, so if this is the velocity, the direction, the point, the center must be at a point which is at a distance r, but it must also lie on the perpendicular to this velocity. But perpendicular doesn't tell you whether it is this close, that far away. So where exactly is the center? At a radius away, right? At a distance r away, where r is known because it's mv by qb. They are combining these two pieces of information. But you always know that velocity is perpendicular to, because it's circular motion, velocity is perpendicular to the radius. So always draw the perpendicular. The center must lie somewhere on that line. Pragalya, I hope this is correct. This is clear. Okay, so when I looked at this velocity, I immediately drew a perpendicular. When I looked at this velocity, I said, let's draw a perpendicular. The point of intersection of the two perpendiculars must be the center. But of course, we don't know how that works exactly. So therefore, you know the radius, you know the value of the radius. So use that. Okay. I know a few of you have some doubts based on the online lesson. I will discuss some of that. Okay. See, remember, this is not a proper magnetism lesson. I just asked you to do a couple of magnetism lessons there as well. I have not yet done magnetism in full depth, and I'm not going to now. I'm going to go to ray optics next class. This is just an introduction for you to say, hey, have you got used to this V cross B? This is very weird, no? This fellow goes in like this and turns around and comes out. Not that obvious. Okay, the force is not obvious. The acceleration is not obvious. And it is three-dimensional. Like, for example, question 3 and 4 is three-dimensional. So just to get you to get used to the idea, I've just started off with this. So don't worry about the online lesson. Don't worry about the questions even here if it is difficult. You will get used to it, trust me. Okay, so we have a system in place. So basically what we are going to do, I'll introduce the concept. I'll go to other topics. Then I'll come back. Your brain will take some time to register. It will take time to basically get used to the idea. Once you get used to the idea, then when you start solving, you will find it becomes a lot easier. Okay, so don't worry about the online lessons, nor worry about the questions now. I want you to put your effort But if you get it wrong, absolutely no problem. This is the first time you are facing something like this. You're going to see this 2-3 times. And when you do that 2-3 times, then you'll see, now it's become comfortable. Okay. So I would like you to get comfortable by the second time I'm teaching this. So right now, I just want you to get used to the idea of cross products, of how do we solve this type of question. Let us see how many people have done question number 3. Okay. Question number 3. Skandan has got this right. Karthik Shankar has got it right. Ritika has got it right. Shruti has also got it right. Roshan Ravichander, Rajendra Prasad, Vaibhav Bomalapalayam. Ayushi, some mistake. Ayushi, just check your answer once more. Kushi has got it right. Kushi Kiran. Vishnu Ravi has also got it right. Ajay Venugopal has got it right. Okay, good. Karthik has also got it right. What a complicated way to write it, Karthik. But yeah, you got it right. Okay. Vaishnav Sudesh has also got it right. Okay. I'm going to wait a little bit more. Those of you who got it right, please try out question number 4. For others, I'm giving you another minute. Okay. So please do try this out. Not very tough. Just think about it and try it out. You'll be able to figure it out. I'll give you a clue. Notice that this fellow has a velocity. Think about it. It has a velocity which has an I cap component, a J cap component, and a K cap, I, J, K. And magnetic field is in the I cap direction. But if magnetic field is in the I cap direction, okay, this way or this way, whichever way is I cap. Okay, let's say that is I cap. And then I also have velocity with an I cap direction. Leave that velocity. Concentrate on the other part of the velocity. Now just think about this. This would have gone and made a circle. It would have come back to the starting point. By the time it comes back to the starting point, the whole circle has moved forward. That's why it would have done this. It would have gone like this. Instead of coming back to this point, it would have started here and gone and landed up there. My question is, what is this distance? How much time would it have taken to do this? That you know, 2 pi by omega. That omega is only determined by V perpendicular. This whole component is perpendicular. First, get that point. Once you get that, what is the omega? You know how much time it's going to take to come back. In fact, the omega does not even depend on V or R. It only depends on the B, Q, and M, right? So therefore, you know how to get the time. But in this time, it would have traveled ahead with constant velocity. So I've given you a lot of clues. Please do solve this. Try it out. I want everybody to be able to now solve this. Okay. So please try this out quickly. Question number Okay, so shall we get started on this question? Question number 3 first. So let us go to question number 3. Okay, so question 3, let's quickly read it. A particle with charge to mass ratio 30 coulombs per kilogram. Okay, is projected from the origin with a velocity of 6 I cap. So its velocity vector is 6 I cap plus 5 j cap plus 12 k cap. Okay, meters per second. In a region of uniform magnetic field B, now the B vector is 0.1 Tesla in the I cap direction. So if I draw the B vector looks like this along the I cap direction. Okay, and the velocity vector has an I cap component and a j cap and a k cap. So basically what I'm going to do is to say it has a 6 I cap, right? So that I basically going to say is in this direction. And then the j cap is like that, the k cap is like this. So the j cap plus k cap will give me a velocity component like that. Okay, so let us just draw the axis. So this is the axis like that. This is of course one axis, and then this is the third axis. So you can see that the velocity has a component along j and k, but it doesn't matter, because really what matters is the fact that if this is velocity, this is B, this is the magnetic field, this is velocity perpendicular to the magnetic field, this is velocity parallel to the magnetic field, and this velocity is 6 I cap. This has j cap and k cap components. Now let's see, if this is the velocity and this is the magnetic field, what direction is the force? V cross B. V cross B is a force like that. And so that is going to make this fellow turn around like this. Okay, so this is the origin. So it's going to make it turn around like that. And it should have just simply come back here. That's where it should have come back if this V parallel was not there. What would be the radius and what would be the omega for this, right? For turning around like this. So this omega we can calculate. Omega is how much? QB by M, right? Q by M into B alpha B. Now Q by M I know is 30. B I know is 0.1. So that means omega is 3 radians per second. To make one full trip round like this, the time period to make this full trip, right, is going to be 2 pi by omega. 2 pi by 3 seconds. But in this time, instead of just going around like this, it would have moved forward. So actually what would have happened is it's not this path that is going to actually travel in. It is going to travel in a slightly different path. It is going to start like this, and it will go up like that. And when it comes back down, it is going to come down here, somewhere here, right? And this distance is what we are interested in calculating. And this distance is V parallel into T. That is the distance that we are talking about here. So therefore, D is V parallel 6 meters per second into the time 2 pi by 3 seconds. And so that is basically 2 into 2, 4 pi meters. Is that okay? So the distance that between successive points. Now what is going to happen after this? It will continue going around and make one more trip like that, and again touch here. Again this will be D. Then again go up and like that. Now I have not drawn this well, but except the circles are moving or separated out as they are coming back. It's like a 3-dimensional circle. Okay, so if I draw it here like this, you can see it. One, it should have come back here, but this is how it's going. It is not becoming bigger. It's not expanding. This is the helix. Okay. So if this is the structure, you can see that to go from here to there, if I just compressed it, it would have looked like this. Okay. Which if I had seen from the top, it will look like a circle. Now to do this trip like this, how much time will it take? Well, what is the rate at which it's turning this angle? Omega. And if it has to come back, it is 2 pi by omega. So that is the time period it takes to make one trip. But instead of coming back here at continuously as this was going on, what it was doing is it was moving upwards as well. So when it reaches this point, actually it's reaching a point little above. When it should have reached this point, it is reaching a point above. It is reaching the same place. If I kind of project it downwards, it is reaching the same place. But I'm just saying that it is not at the same height. And similarly, instead of reaching this place, it is doing that. If I just compress this loop, if I not compress this loop, compress this path down, you would have seen a nice perfect circle. And similarly, the second path will look like that, second round, third round, etc. That is the shape of the helix. Except now we have, of course, drawn it horizontally. Okay, so I know it will come back to the x-axis. How do I know it's coming back to the x-axis? Because it was at the origin in the beginning. Okay, since it was in the origin, it has to come back to the same point. Except now that point is no longer at the origin. It has moved along the V parallel direction, along the B direction. But along B direction is x-axis. So will it keep coming back to the x-axis? Yes. Will it keep coming back to the same point on the y-axis? You can't say that, right? But it will come back to the same y height because it's going to keep doing these circles. I hope that is clear. So this is how we solve this problem. Let us go on to question number 4. Can you all please try out question 4? Try out question number 4. I'll give you another 2 minutes to solve this. That's a little bit more harder. Okay, so I'll give you a clue also. Same principle. Just look at what is... how is it going around in a circle? Do the circle part independently of the movement of the circle. Like you have in, let us say, projectile questions. You would say X motion and Y motion, you will basically say they are independent. The same way, this is 3D, so helix. So you say there's a circular motion, circular, and the motion forward, X motion, X direction, horizontal, whatever, they are independent. These two are independent. So you can do this without worrying about that, and you can do that without worrying about this. So do them separately. It is actually one circle. As the circle kept moving, that's why you kept getting this helix. The helix is just a circle. What is happening in the circle? Just simply project it, you will get that circle. Okay, so do that separately, do this separately. Try out question number 4. Once you get it, then we can go on to the next question. Those who have finished question 4, please start doing question 5 and so on. But question 5, I need to do a little more theory. Okay, but not very complicated. If you have electric and magnetic fields, both will play a role. That's all. So can you first do question 4? Then we can discuss the next concept. Aparna has asked, what will happen if there was an electric field parallel to the magnetic field? Then what is the type of path taken by the charge? Well, if that was electric field parallel to the magnetic field, that velocity which was already parallel, right, will now become faster and faster. So it will be uniform accelerated motion along B direction, but it will be a circle along the perpendicular direction. There will be a, in the XY plane, it will be perpendicular, but in the not XY, YZ plane, it will be perpendicular for the previous question. And in the X direction, it will be like a accelerated motion, uniform accelerated motion. Okay, we will be discussing electric and magnetic fields together a little later. I mean, later as in like next question. Nagvekar has asked, does the helix expand? No, not in this case. The helix does not expand. Is it possible for the helix to expand? There must be something that makes it faster in the perpendicular direction. Then you can get a fast expanding helix, but not now, because right now what will happen is that the speed remains constant, so the radius remains constant. And so basically it will just keep going around, except it's also moving in that direction. So helix is not becoming larger. It's not becoming wider circles. It's the same circle size, but it is just moving upwards. So think of, see, if you had a slinky and you expand it, that is a helix. Okay, that's not a spiral, that's a helix. So if you take a slinky and you do that, then you will get that rings, no? That is a helix. Okay, please do try out question 4. Okay, so shall we start doing question number 4 now? Okay, and so question 4 is also a helix question. So, but this is a question where we have the axis. So let me just get the axis here. So this is y-axis, this is the x-axis, and this is the z-axis. Okay, so this is the I cap direction, x-axis, j cap direction, which is the y-axis, and k cap direction, which is the z-axis. So I cross j, you know that is going to give you k. Okay, so we have been told that there is a magnetic field which is 0.2 Tesla I cap. So magnetic field is in this direction. B is 0.2 Tesla I cap. So it's in this direction. So any velocity in this direction won't matter, right? And so we also have the velocity of the particle. It is 4 root 2 I cap. So this direction, it is 4 root 2 I cap meters per second. And 2 pi j cap meters per second, which is this way. 2 pi j cap meters per second, which is that way, right? And the particle starts here. So let's take the particle. It starts here. So this is the velocity that matters. So if I had a velocity that points like this, V points like this, and B points like this, let's think about V cross B, V, B. So what is V cross B? V cross B, don't look at my hands. V cross B is pointing away from me into the board. Okay, so this is the direction of the force. So the force is going to be like that. Okay, so that you should calculate. Is the charge positive? We are going to assume the charge is positive. Okay, it's also given charge to mass ratio is 5 pi coulombs per kg. If it was negative charge, you should have said minus, because mass is not minus, right? So Q by M is 5 pi. Q by M is 5 pi. The force is in this direction. Velocity is like this, force is like this, so it's going to bend in that direction. See, whenever you have velocity like this and force is this way, it will bend like this. And if the force is that way, then it will bend like that. Right? So basically, you know that whichever direction the acceleration is, that is the direction in which the velocity will bend. So this is going to bend like that. That is basically minus k cap. So this fellow is going to go around and go around like that, minus k cap. If I was thinking about a circular path, this is what it should have done. Okay, so this is like the center of the circle. So let's think about that. I have not drawn it very well, but center of the circle must be along the k cap direction. So let's draw it like that, goes under and then comes like this. So this is the center of the circle. This is the center. Okay, so is that clear to everybody? This is the center. So this is radius r. Okay, now we know that. So if I draw this circle, obviously this is not the path. This path, think of the circle, and the circle itself is going to move. So let me draw the circle here separately. Okay, now which part of the circle were you in at the beginning? Here. So this was the original part where the velocity was like this. Now, after some time, it's going to become this way, then its velocity is going to become like that, etc. But what we know here is that this is that radius r. This is the origin, the 0, 0, 0. Now, we don't have the I cap is always 0 here because we are not changing it along this direction right now. Then we will move it that way. So this point will also be 0, something, right? So, but this is r. R in that direction means this point is what? This point is x-axis 0, y-axis 0, z-axis is minus r. Now, enough of all this. Let us think about what is omega. What is omega? Q by m into b. What is b? 0.2 Tesla. Q by m is 5 pi. So 5 pi into 0.2. So that is going to give me 1 pi, right? Omega is pi. Pi radians per second. That is omega. Now, what is omega into time? That will be the angle that is covered, not the angle of entry. The angle that is covered is omega into t. Is the time given? It is given, no? Half a second, 0.5 seconds. So that means it will have covered an angle of pi by 2. From where you start, if you make an angle of pi by 2, this is where you will land up. this point is equal to this point here. The velocity there would look like that. The velocity will be 2 pi j cap. 2 pi minus k cap. It will be in the k cap direction, minus k cap. But my question is more about the coordinates of this point. What is that point? Let's call that point as B. Let's call this point as A. So what are the coordinates of point B? It is R like this and R like that, no? So that means the I is 0, 0. And you've got a j cap, which is j cap direction. You've moved up R because you're moving up R. This is moving up and is going backwards like that. So this is R, comma, minus R. Understood? And because you're going to also move in front in this time, this point will not be here anymore. This point is actually going to do this. So let us draw the actual path. It's going to go like that. Okay. And this is the point where it is going to be. And so if you look at this, right, this will be V into T. This is going to be V into T. So this displacement is 4 root 2 into time, which is half, 2 root 2 meters. So this is the point I'm interested in. That is, let me call point P. What are the coordinates of point P? Instead of 0 r comma minus r, it will be 2 root 2 because it has moved also in the I cap direction, 2 root 2 comma r comma minus r. So I know what this point is. Therefore, I know what the vector from the origin to that is. Therefore, I know what the displacement is. First thing I need to know is to calculate r. What is r? R is v by omega. V by omega. Do I know what the velocity of the particle is? It has been projected with an initial velocity. 4 root 2 was this velocity that I don't know. This velocity is 2 pi. Oh, that is already given. 2 pi. And omega is pi. So that means r is 2 meters. So we know r is 2 meters. So point P is 2 root 2 comma 2 comma minus 2. Okay, by the way, if you had taken it in this direction, the actual position you would have got wrong. Your answer overall may still be correct, but you have to do this carefully. So it is this direction it's turning in. Okay, so because the center is in the minus k cap part of the axis, you'll also see that this is how it is turning. And so this is the position. Therefore, now if I want to look at the vector from here to there, let's draw that vector here, this vector. This is our displacement vector. So how much is the displacement vector? It is the position vector of this guy. So it's 2 root 2 I cap plus 2 j cap minus 2 k cap. Minus 2 k cap. And so magnitude of this displacement is root of 2 root 2 square. 2 root 2 square is 8 plus 2 square, which is 4. Plus minus 2 square, which is also 4. So this is 8 plus 8, 16. Root of 8, 16 is 4. So this is 4 meters. So that means this distance, what is the displacement magnitude? The answer is 4 meters. I can see that many of you have got it right. Okay, so that's very good. Let me just quickly see it. So here, how many people have got this right? Skandan got it right. Vaibhav has got it right. Srinidhi, you got a 10 power 17. I don't know where that came from. Where did that come from? Did you put a Q inside? Or did you take a proton or electron or something? Okay, I don't know where you got the 10 power 17 from. But, okay. Many of you have got it right. Some of you have also got it wrong. Well, after this, quite a few have got it wrong. Okay. Okay. Vedram has also got this right. And Vishnu Ravi has got this right. Very good. Roshan Ravichandar has also got this right. Anirudh has got 3.9. Did you do some approximation somewhere? I don't know. Yeah. Anyway, let us now go on to the theory for the next question, which is important. So far we have been only focusing on magnetic fields. So what happens if you have electric and magnetic fields? Suppose you have both electric and magnetic fields. Notice that a charge would have a force, electric force, will be Q times E vector. And magnetic force, I'll call it FB, is Q V cross B. What will happen if both electric and magnetic fields exist? No problem. The force is just Q times E plus V cross B. Okay, this is called Lorentz force equation. This is just telling us that a charge is going to have a force because of the electric field as well as the magnetic field, and therefore the forces just simply add up. So this is called Lorentz force on a charge. Okay, so Lorentz force on a charge in the presence of E and B. So when both E and B are there, Q times E plus V cross B. Q times E plus Q times V cross B, just superposition, just simply add the two up. So I hope this is clear. So suppose I had E like this and B also like this, and a particle was at rest, only QE is going to act. If the particle was moving like this with a velocity V, again V cross B is 0. So again the force on this is just QE. Okay, so if E is parallel to B, then this is basically if V and V is also parallel to, all three are parallel, then only force is QE. And so acceleration is QE by M. It's going to be like straight line motion. The B won't even matter because always the velocity will be in this direction. Now let us think about what happens if I had a situation where this fellow had a velocity like this, and you had E and you had B. But the velocity was like this. Well, V cross B is going to point which way? V cross B is going to point into the board or into the screen. So that means there is a force like this. This is QV cross B, assuming VQ is positive. And then you will also have a force like this, which is Q times E. So that means your net force will be something like that, F net. So it's going to feel a force in this direction. Okay, but the QE will do work. QV cross B won't do work. So when you're looking at the force, the net force involves both Q times E plus Q times V cross B. When you do F dot V, because F dot V is power, work done is F dot S, per unit time is F dot V. So if I did F dot V, Q times E dot V need not be 0, no? But plus V cross B dot V dot V will always be 0 because this is perpendicular to V, this is dotted with only because of work done by electric field, electric forces. The magnetic forces anyway never do work. This is work done per unit time. Okay, this is a power transferred by electric forces. Anyway, so I hope this is clear. So the force is in some weird direction. So will it go in a circle? It might not. It depends. Now, so far I've assumed E and B are in the same direction. Doesn't have to be. In many cases. For example, electromagnetic waves, generally E and B are perpendicular to each other. So many problems will be E and B perpendicular to each other. Now, if you had an object moving with the velocity in this direction, what is going to happen is E is going to make this go faster. But B, V cross B, what is the direction for V cross B? It is going to be like this. So that's going to make this fellow go around in a circle like this. But then E is going to make you go faster. So you're going to have a combination of this and E. So you will end up not going in a circle, but you will be in this plane. And so your path is going to be probably like this. Maybe it will bend around. So you'll have to check that out. So if this is reasonably complicated, if I left it at rest, I know that it's going to be a path called a cycloid. Because if I left it at rest in the beginning, B won't matter. But because of V, I'll start moving. And as I start moving and gaining velocity, B will start to turn it. And that will happen all the way till I come back to this point. This point I will stop. Then again, I will continue. This is called a cycloid. Okay, so if E and B were perpendicular to each other and you left it at rest, I know the path is this, but I need not have left it at rest. I could have left it to the velocity. Or I could have left it to the velocity that looks like this direction. Okay, the component of velocity in this direction, B will not affect. And so you'll have to basically take everything into account. All of it just simply comes out of this. It looks messy, but don't worry. Situations will be given which will be reasonably simple. So just simply look for E, look at V cross B, just add the two up, superposition. Okay. Now I would like you to try out question number 5 And if you finish question 5, please try question number 6. Both of these, there are electric fields. Okay, so in the fifth question, I have not given you the direction of the electric field. I have to give you the direction of the electric field. It has a direction k cap. Okay, that is 400 k cap. Electric field is 400 k cap. Question 5. E should have been 400 k cap newtons per coulomb. This is, I forgot to write the k cap. Okay, so 400 k cap. Can you quickly solve question 5 and then go to question 6? Sorry again. I was just looking at what was the original question. Yeah, it could be K cap. There is no problem. So I would like you to do both. Okay, part 1, do it for E basically being 400 K cap. Part 2, do it for E being 400 I cap. Simple. Both questions are reasonably simple. So basically 400 I cap and 400 K cap. I had originally tried 400 I cap, but now do both. So part 1 for question 5 with 400 K cap, part 2 for 400 I cap. So this is regarding question number 4. There are a couple of doubts. Okay, so I'm just going back to question 4. So in question 4, Ritika is asking, why should V parallel times T be used? See, this is actually just going around in a circle, right? Here, this is just going around in a circle. But actual path is a helix because this is how it's going to go. So where will it be? It would have gone in a circle. So it's like it's going from here to there. But while it is going around in this circle, it is also moving forward. So the forward part is, this is basically V parallel into T. This is V parallel into T. So this is important because this is what is telling you how much it's moved forward. Okay, otherwise it's just going in a circle. Okay, and so displacement is this displacement plus that displacement. That displacement was in the I cap direction, 2 root 2 I cap, right? Because that is 2 root 2 meters. But I just found the coordinates, therefore I can easily find 2 root 2 I cap is the displacement like that. If you had just used these two, you'd have got 2 root 2 as your answer. But that 2 root 2 is only telling you the displacement here. If you had just taken, so the helical path, you've just flattened it out and you just did the question on the circle. And you're just doing this displacement. But this is not where it is. It is actually, while it should have been there, it has actually gone there. See, you think of it like this. If you think it's going in a circle, but before it reaches this place, it's not reached that place ever. It's actually going like this. So the real displacement is this. You must do this arrow. Understood? Because this arrow is only telling you this part, like as if it's in a plane. This is 3 dimension. So you'll have to spend little time. I know that's confusing. So that's exactly why I want you to learn this little earlier. See, whatever is hard, like integration. Okay. Is it hard? Not really. But if you don't learn integration early enough, like calculus, differentiation and integration, you start learning it early. It's very, very useful because once you learn it, your brain takes time to get adjusted to it. Vectors, very, very important. That's why my very first class in 11th standard, I started vectors because you can wait, you can do it a little slowly. But the later you do, more time your brain is going to take to adjust. Certain things, it's not about the concept. Some things, it just takes time for your brain to get used to. Vectors is one such thing. Okay, cross product, like for example, magnetism will be one such thing. After some time, you'll find it's very trivial, just simple calculation. But in the beginning now, it's going to look messy. Integration, differentiation. Okay, all these are concepts that if you start learning early and then take your time, let it slowly sink into your head. Then you will find that it is comfortable. The same way, magnetism with all this 3-dimensionality is a little messy. Spend time, do it, relax, go to other topics, come back. Second time, your brain is now saying, oh, now I know what it is. Okay. Some of you might have read Harry Potter. Okay. He had a lot of trouble basically throwing this, what is that called? Patronus charm. He kept one full book. He was basically constantly taught to do the patronus. The reason he was able to do, and he did it in a very difficult situation, he was able to do because he remembers that he has already done it. So if you have already done it once, the second time becomes easy. Okay, so there, of course, it was a little bit of time travel nonsense that happened. But if you leave that out, the basic idea that if your brain knows that you did this earlier, second time, it basically is a lot more comfortable. Same principle here. If you have now attempted, don't have to answer, you don't have to even get it right. But if you think like this, next time you see a question, your brain will say, oh, this I remember. And the second time you will be able to do. First time, everybody finds this hard. Okay. So it's not because it's hard. It is because it's very unfamiliar. Okay. It's 3-dimension. It is cross product. So, and then there is forces acting here and some messy stuff. It's going in a circular, but it's not even regular circle. It's a helical path. So you have to think about all that. And that is reasonably new. That's all. Okay. So shall we go on to, I was trying to look at doubts, right? So that was Ritika's doubt. Vaishnavi was saying, is 2 root 2 wrong? No, 2 root 2 is wrong. That is only giving you the displacement along the YZ plane. So you need to do a little more than that. So that 4 meters is the actual displacement. Pragalya is asking, will V cross B not change during its path? Because as Q is moving, its velocity changes due to the acceleration produced by V. Very good point. Very good point. Yes, the velocity will change because of the electric field. We are talking about at this instant when it has this velocity and has this magnetic field. In general, well, if, for example, the electric field only change the value of the velocity along B, it won't matter. Then it won't matter. Okay, that's why I'm saying if electric field was along B, then it won't matter, because then it will only change the value of the velocity along B. But in this case, electric field is not along B. So yes, over time, electric field will change the velocity, and when it changes the velocity, the acceleration will also change. So the question is actually asking you, when the velocity is at that particular value, what is the acceleration? Okay, so don't have to find the acceleration in general, you have to find the acceleration at the instant given. But it's a very, very good question, Pragalya. Okay, I hope everybody is clear about that. The one time where it won't matter, the acceleration won't matter, is because velocity and B are in the, electric field and the magnetic field are in the same direction. If they are in the same direction, anyway, any component of velocity along the magnetic field won't matter. And so electric field will only produce it because it's only going to give you velocity extra. It will add delta V along E, because that is the direction of the force. It won't matter because that will not contribute to the perpendicular direction to B. So for that one case alone, it won't matter. For question 5, it should matter. Okay, for question 5, question 6, etc., it will matter. But we don't want to worry about it because we are looking at that particular instant for question 5. A lot of people have answered question 5. Let me see. Magnitude is all I've asked. Magnitude is all I've asked. Yeah, many of you have got it right. Many of you have got it right. Some have got 10. Some 10 is wrong in somewhere. Okay. So quite a few have got this right. So shall we go ahead and start solving question 5? Let's solve question 5. And then I'll give you time for question 6. Okay, so that is question 5. And this is part 1 and part 2. Okay, so let us start with question 5. Let me read the question out. A proton is moving with a velocity of 5 I cap. So whenever you have a proton, you just simply say the charge of the proton is 1.6 into 10 to the power of minus 19 coulombs. Mass of the proton is 1.67, but I will just call it 1.6 into 10 to the power of minus 27 kilograms. Okay, so this is the charge of the proton and this is the mass. So Q by M ratio, which is the important thing, you can see that this will almost cancel. It doesn't really cancel. So it is 10 to the power of 27 minus 19. 27 minus 19, because you're doing Q by M. So technically it should be 1.67, but I'll just take this way. So what is 27 minus 19? 27 minus 17 would have been 10. Okay, minus 2. So that means 10 to the power of 8. So Q by 10 to the power of 8 coulombs per kg. Okay, nobody writes the units, they'll say SI units. Okay, let us now go on. A proton is moving with a velocity. A proton is moving with some velocity. 5I plus 4J. So something like that. 5I cap plus 4J cap meters per second. And in a region with electric field, so right now there are 2 electric fields. One is in the K direction. So we'll leave the electric field. So let's look at the magnetic field. Magnetic field is also like this in some direction. Magnetic field is 0.2 I cap plus 0.1 J cap, Tesla. And so if I do V cross B, okay, or Q V cross B, but right now I'll just do V cross B. What is V cross B? I cap cross product, of course, is 0. So I cap, J cap cross product. What is I cross J? It is K. So 0.5 K cap. Okay, and then 4 cross I. So this 4 into 2 is 8. So that is 0.8. But J cross I cross J is K. J cross I is minus K. So if I put a K cap here, I should put a minus K. And J cross J, of course, is 0. So this is going to give me minus 0.3 K cap. This is V cross B. Now, if I just look at what the charge is, the charge and the electric field is, it's 400 K cap, right? So if I take 400 K cap, and I have to be a bit careful here. This was kilometers per second. This is not meters per second. It was kilometers per second. So that should have been multiplied by 100. Sorry, multiplied by 1000. So into 1000. Otherwise, it made no sense. No, this was 400 and this is 0.3. So this was kilometers per second. And so this is minus 300 in SI units, minus 300 kcap. And this is, of course, 400. So we can now get to the first force. Force for the first case. Force is Q. Okay. And force by mass will be acceleration. So Q by M into, okay, E plus V cross B. But remember that you have to do this with vectors. So it is Q by M, but you know Q by M is 10 power 8. E is 400 K cap, 400 K cap minus 300 K cap. And so that gives me 100 K cap. So 10 to the power of 10, right? 10 to the power of 10 meters per second square would be the acceleration. So the acceleration is 10 power 10 meters per second square. That is like 10 billion meters per second square. A huge acceleration. Okay, unbelievable acceleration. Of course, it's a proton, so it's not a problem. Protons can have such huge accelerations. Okay, so the second part is F by M is Q by M, Q by M. But E vector is 400 I cap. So E vector is 400 I cap, 400 I cap, and this is 300 K cap. And so therefore this is A vector. And so if I want magnitude of A, this is A vector's magnitude. Similarly, if I have magnitude of A vector, that is Q by M, which is 10 to the power of 8, root of 400 square plus 300 square, which is of course 500. Okay, this is 500. So 5 into 10 to the power of, wait a minute, I think I might have made a mistake here, right? No, this is 100, this is 100, whereas this is 500. 5 into 10 to the power of 10 meters per second square. Okay, so acceleration magnitude is 50 billion meters per second square. 50 billion meters per second square is the acceleration. Massive accelerations, both of these. Okay, right. So can you now try out question number 6? Please do question number 6. So question number 6, there is a region of space. E dot B is 0, so that tells you something. Magnitude of E is given, magnitude of B is given. And a charged particle is moving with a constant velocity. A charged particle is moving with constant velocity. That statement is very important. By the way, question number 6 comes up very often in NEET. It comes up very often in, they may not give it to you in this format. They may tell you some more information. They may give it to you in this format. You don't know. But this kind of a question, that type of a question comes up very, very often in NEET as well as JEE mains. So you should definitely know how to do question number 6. Think about it. The velocity is constant. That's basically the key. Thanks, Gayatri, Rajesh, and Srivatsa. I know that I made a mistake in that kilometers per second, but I think I corrected it right on time. Okay, so thanks for pointing it out, though. Can everybody now do question 6, please? Akhilesh, you have said that you got a different answer when you do it with kilometers per second square. You can't do that because V cross B is kilometers, but E is in SI units, right? Meters. So therefore, E may not show you that it is in meters, but it is in meters. Okay, it's equivalent of having this in meters. So when you say E is 400, it is newtons per coulomb. That is not kilometers. So if you're adding up two numbers, this was in kilometers, but that was not, that becomes messy. So you'll have to then convert E. If you did not convert V, then you have to convert E. So, okay, so most people won't do that. So therefore, that's probably the mistake. That is for question 4, I think. And Ayushi has said second part, EI sin I and B is in I and J. So we shouldn't worry about the velocity. Which question are you talking about, Ayushi? Oh, you're saying the second part, E is I cap and B is also I and J. So shouldn't we, this is at that instant. So the acceleration, Ayushi, is basically being asked at that instant. Yes, of course, you should worry about it because over time, E will change the velocity. I mean, so therefore, B will also get affected. So let's see how many people have done question 6. I don't think many people have answered question 6 yet. What has happened? So, okay, I'm going to give you a minute more. Come on, quick. So I want to go to the next concept. Okay, so can you please quickly do question 6, everybody? Okay, so shall we get started on this question? Not too many have answered, but yeah, I think we can go ahead. But Yeah, few people have not answered, but let us get started. Otherwise, we won't finish this. So let us go to question number 6. Okay. So let me start it on a new page. So this is question number 6 here. In a region of space with E dot B is 0. So what does that tell you? That is E perpendicular to B. Sorry, E perpendicular, not this symbol. E is perpendicular to B. Okay, so that we know because E dot B is 0 as vectors. And magnitude of E is given. Magnitude of E is 40 newtons per coulomb. I won't write that. Magnitude of B is 2 Tesla. This is newtons per coulomb and 2 Tesla. A charged particle is moving with a constant velocity. What does that mean? How can a charged particle move with a constant velocity? It keeps moving with a constant velocity. How is that possible? Well, first of all, there might have been a magnetic force on it. See, 2-3 possibilities. So if charged particle is moving with constant velocity, velocity is constant, then acceleration is 0, which means net force is 0. So that means Q times E plus V cross B must be 0. Now Q is not 0 because it's a charged particle. It says that it's a charged particle. So E plus V cross B must be 0. So electric force and the magnetic force must be opposite to each other, first of all. But how is that possible? Because if this is the velocity, V cross B is definitely perpendicular to the velocity. It is perpendicular to the velocity, right? So if the velocity was like this, it has to be perpendicular to the velocity, which means it has to be somewhere in this plane. So if the velocity was like this, it has to be in this plane, right? It could be this way, this way, this way, anything. But let us say that V cross B was like this. Why would like this? How would that be the case? Let's see. So if velocity is like this, B was coming out of the board, velocity is like this, then V cross B will be pointing down. So it was coming towards me. So if I say B was like this, B is pointing this way towards me, V cross B will be pointing downwards. I just took downwards as a direction. It could have also been like this, it could have been like that, doesn't matter. But I'm just saying if you pick downwards, B would have been this way, right? B would be like in the K cap direction. I cap, K cap direction. And E has to be like this. This has to be the direction for E. And you can see that E and B are, E is up like this and B is pointing towards me, right? So E and B are like this. Does it satisfy E perpendicular to B? Yes, it does satisfy that, right? Because it's constant velocity. Okay, now let us think about the next part. Find the smallest possible speed for V. Smallest possible speed for V. Okay, so basically I want E to be opposite to this, right? I want the acceleration to be 0. I want E to be opposite to this. What will be the smallest possible speed? Well, think about this. VB. By the way, V and B need not be perpendicular to each other. Why? Because it's also possible that instead of being like this towards me, B could have had a component like that, right? So it could have been like this. B could have been like this. You can think of one component this way and one component of B in this direction. And then this component doesn't do anything. Anyway, there are no forces acting on it, right? And E and B are, of course, perpendicular. And if you look at V cross B, the force will still be like this. V cross B has to be like this. Okay, but for V cross B to be like this, it doesn't mean that the B has to be this way. B could be anything in this direction. Well, it can't be in that direction because if it was that direction, V cross B will be pointing upward, but you could have had a whole range. So if I saw this from the top, let's say this was the velocity V, and I was looking at it from the top, B vector could be like this, could be like this, could be like this. It can't be like this because if it was like this, then V cross B will be pointing upwards. So it can be all the way from here till there, not that line, but somewhere till there. I have said that it should be like this. Like this basically means towards me. Okay, I'm looking at a projection from the top. Okay, 3-dimensional view. So this is as seen from the top. As seen from top. You have to always do that kind of projection for three-dimensional cases. So I am selecting this because if I chose any other B, you will get V into B into what? Sine of the angle between them. So remember, V cross B is VB sine of the angle between them. That you want it to be minus E. Okay. Well, as numbers go, just equal to E. And so if you want V, you can say it is E by B sine theta. But if I want this to be the minimum value, sine theta should be the maximum value, which is 1, which basically means that it has to be perpendicular. So B has to be like this. By the way, if B was like this also, it is perpendicular. If B was like this also, it would be perpendicular. But you want it to be this way. You want it to be E like this and B like this. So that all three X, Y, Z axis will all basically be, if I think of this as X axis, so let's just quickly get the axis in place. Okay. And so this would be, this is the way it looks. So this is the direction of the velocity. This is E and this is B. Everything is perpendicular to each other. They are all perpendicular to each other. E has to be perpendicular to V, no problem. That you can understand. Okay. B need not have been it, but for minimum value, for minimum value, V minimum is E by B. Right? Because sine theta must basically be 1. So now if I do E by B, it is 40 by 2. So it is 20 meters per second. So this is the minimum velocity with which it must move for this to happen. I want to again show you a little bit more about what exactly this question is all about. Okay. Why is this question so important? So let us quickly go through a situation where I have a capacitor. Okay. Now you have a capacitor, for example, for TV channels, like not TV channels, TV. So old TVs like this CRT monitor TV. Let me just get rid of that. So this is our CRT monitor TV. Okay. So something like that. What we replaced it with LCD TVs. So you have an electron that is basically released from here. This is a capacitor with a plus minus. Okay. So as the electron comes in, this capacitor can sway this. It can make this bend down or up by changing the field. But you also can make it move left, right by having a B field. So there is also a magnetic field. There's a magnetic field and there is an electric field. And so with that, you can actually make this fellow go and hit this or make the electron go and hit that. So all these places, you say you can get that light. So this is already like a colored, there's a chemical that is there. And when the electron goes and hits it, this particular thing sends out a spark, right? Basically, you are scintillating this screen. And so that basically produces your TV image. The TV image is therefore run by a capacitor and a magnetic field and that you are changing. So that's basically what I'm looking at here. So imagine that you have a capacitor. Okay, so when I usually send a charged particle, let's assume I'm sending a positive charge. This positive charge is going to go down and bend. So it's going to go like this, but it's also going to bend because of this process, right? So it is going to go straight till here. And then from here, it's going to start bending like a projectile, right? So it's going to go down because there is a field that is pulling this fellow, pushing this fellow downwards. QE. But now if it is possible for me to put in a B field that will give me a QV cross B, what is going to happen is that this point, instead of going and landing up there, may end up landing up there because QV cross B may not be just right enough. So it may go up a little bit. But if I can make this go up in such a way that there's no deviation at all, it just lands up right in the middle. Okay, wherever it started, it without deviation lands up there. That means V cross B is equal to E, right? That's when this will happen. So for example, the velocity is this way. If I want V cross B to basically point up, you're talking about a B which is in this direction or which is that direction. That doesn't mean upward, that means this way. Okay, so think of it like three-dimensional case. This also gives me V cross B upward, but this is not the minimum V. But if you made the V and B, E is downwards, no? Electric field is downwards. If I made the magnetic field perpendicular to the electric field, then I can adjust it in such a way that V cross B is equal to E. If it went straight with the velocity, particular velocity, it will just go straight. You can use this for many things. You can use this for a velocity selector. Like imagine that I had a blockade here and a small tiny hole. Okay, that means only if I went in a straight line, I can escape, right? All other things won't escape. So I want to keep it straight. Anything which came with different velocities will start to deviate. Only the charge which came with the right velocity. So if I had like velocity v1, only the right velocity v1 will manage to get out, where v1 cross b is equal to e. So you can use this as a velocity selector. You can use this configuration of e like this and b perpendicular to e. This configuration is something that is very, very common. And so people will give you that as a question. One of the cases is qv cross b cancels out qe, which means the net force on the particle is 0. The particle moves with constant velocity. Okay, I know that we have kind of run out of time. I wanted to do this force on a conductor, which I have not done today. I should have, but I have not done today. So you can't do question number 6, 7, 8. But if I start force on a conductor now, it's going to be quite long. Okay, because it's already 8:30. So we will stop now. Okay, I hope you got a general hang of the idea. You can try out some of the questions that have been given here. Okay, I, L cross B will be the force on a conductor, but I have to do that more carefully later. I'll come back and do magnetism. Next class, we are not doing magnetism. I've just done magnetism to get you to start seeing how to do these three-dimensional cases and how to do V cross B. Okay, so I hope you have understood that. Spend some time, think about it, and then let it sink into your head. It will take some time for things to settle down. Okay, next class, we are going to start with ray optics. Okay, so I'm going to start with ray optics. That will be easy, fun. You have learned it already. But we are going to do a little bit more complex questions in ray optics. So we'll start with that. I would like you to start doing the online lessons on ray optics. Magnetism, just leave it, let it hang for some time. We can come back to magnetism because I want your brain to start thinking about magnetism the way we have started. Hopefully, you will find that over time, you will find that it's comfortable, and then we can go back to magnetism again. So next class, we are going to start with ray optics. Okay, thank you. So we'll stop for now. So we've done up to question 6. Yeah, question 7 onwards, you lesson where I've already described a little bit about how to do force on a current carrying conductor. I'll come back and do that next time when we start magnetism, which will be probably month end or something. We'll be starting magnetism again. First, I will finish optics, ray optics. Wave optics we'll do a little later. So I'll do ray optics. I might come back and if necessary do a little bit on capacitance, or we can go to magnetism and then come back to capacitance later. Okay, we still have something to do more with capacitance, but that we'll do a little later. Okay, see you.